Hi, we are going to do a quick video on hypothesis testing for a single proportion, and we're going to look at how to use StatCrunch to do this also. If you have not learned just the basics of hypothesis testing, you will first want to go back and watch my video to learn just the basics of hypothesis testing before you do this video. So to do a hypothesis test for a claim about a proportion, we are going to use the normal approximation for a binomial distribution. And to do that, we have these three requirements that must be satisfied. First, we need to have a simple random sample. Second, we need to make sure that the conditions for a binomial distribution are satisfied. And third, we want to make sure that n times p is greater than or equal to 5 and n times q is greater than or equal to 5. Now p represents the probability of success that is associated with our binomial situation. Q represents the probability of failure, so the complement of p. And then n represents our sample size. Now when we set up our null hypothesis, our notation, we're going to have the h sub 0 with our semicolon, and then in this location we are going to have a p, which stands for population proportion, because that's what we are testing, is the proportion, and that's going to be equal to some value. Now the null hypothesis, that's going to be the claim that we are trying to prove is wrong. Our alternative hypothesis can take our three different forms. Now notice our setup here. We have h sub a to represent alternative hypothesis. Sometimes this will be h sub 1 for some books. Just depends on the text that you're using, so those are interchangeable. And now notice, again, I have p, so I have my population proportion symbol no matter which of the three alternative hypotheses I have. And then here, my numbers will be the exact same as the numbers up here. So the difference between these alternative hypotheses is the symbol, and the symbol will typically come from the text or from what you're trying to show. So if you're just trying to show that the population proportion is different than what the original claim is, then we would use not equal. If you're trying to show the population proportion is less than the claim, you would use the less than symbol. And if you're trying to show that the population proportion is larger than the claim, you would use the greater than symbol. Now, in order to do a hypothesis test, we are first going to compute what is known as the test statistic. Now, in order to do that, we have this formula here where we're going to be computing a z-score, because remember, we are using the normal approximation. So our z-score is going to allow us to look up some different values on our normal distribution table. P hat, that represents the sample proportion. Okay, and then p right here, that's our population proportion, and that's going to come from our null hypothesis. And then down here we have p and q again, and then we have our sample size of n. Okay, once you get your test statistic computed, then you would have to choose whether or not you would want to do the critical value method or the p-value method. Both of those methods will produce the same final result. It's a matter of your preference or maybe what technology you have available to you. So let's look at an example. This is some information I found about college debt some time ago, and we are going to use this very first statement here where it says in 2012, 71% of all students graduating from four-year colleges had student loan debt. Okay, so that's going to be our original claim. What I want to do is I want to test if the proportion of students graduating from four-year colleges with student loan debt has changed since 2002, and I'm going to use a 0.05 significance level. Okay, I tell you that I surveyed 135 four-year college graduates of the class of 2019 and found that 93 of them said that they did have student loan debt. So that's kind of my situation. Now, before I jump into doing my test statistic, I want to make sure that my requirements are satisfied. So I want to make sure that I had a simple random sample. Well, the information I gave you doesn't really tell us how the sample was gathered, so we're going to assume that's true. I have to have the conditions for a binomial situation. So we have only two outcomes. Either they did have debt or they did not have debt. We are going to assume that the probability of success of a student saying they did have debt was the same from one student to the next student, and we're going to assume that we had independence of trials. So we're going to say that our binomial conditions are satisfied. And now this last one, we have to check, is n times p greater than or equal to 5, and is n times q greater than or equal to 5? Well, in this situation, my n is 135 because that was my sample size. My p, the probability of success, well, that comes from right here in my original claim, because my original claim is that the proportion that do have debt is 0.71. And that will now allow me to find q. So q is the complement of p, so it would be 1 minus 0.71, which is going to give me 0.29 for my q. Now I can do a simple calculator exercise, and I can take 135 times 0.71. When I do that, that's going to give me 95, which is well over 5. And then I can take 135 times 0.29. So this is n times q, and when I do that computation, that gives me 39, which is well over 5. So both of these requirements there are also satisfied. Since all of our requirements were met, we are going to go ahead and do our hypothesis test. Now we're going to start out by writing our null and our alternative hypothesis. So my null hypothesis is from my original claim, which is that the proportion that have college debt is equal to 0.71. My alternative hypothesis, if we look at the text, it said that we were just interested in if it had changed. So that didn't indicate whether we were thinking it was higher or lower. That is just a matter of, is it different? So we want to go with the not equal symbol. Now notice right here, my numbers, my 0.71 and my 0.71, that does not change from my null to my alternative hypothesis. Now with this, my alternative hypothesis, because it's a not equal, I'm going to end up with a two-tailed test, which will become relevant later. So I've got my null and my alternative hypothesis. I know that I'm doing a single proportion z-test, so now I can go ahead and I can do my test statistic. Before you start doing this computation, I would recommend listing all of the things that we know in notation. So I know that my sample size, my n, was equal to 135. I know that p, from right up here in my null hypothesis, is equal to 0.71. I know that q is the complement of that, which is 0.29. I know that p hat is going to be equal to the 93 that said yes, they do have student loans or student debt out of the 135 that I sampled, which is approximately, I'm going to round mine to 0.689. And then I know that my alpha is equal to 0.05. So I think those are all the values that I know from my text. So when I come to do my test statistic, I can go ahead and plug in my appropriate values. So I need to take my p hat minus p, so I would have 0.689 minus 0.71, divide that by the square root of p times q divided by n. Once you get that computation done, you should turn out to have a test statistic of negative 0.5377, and then the decimal keeps going. So if, depending on the technology that you're using, you may not need to round to that, but if you are looking this value up on a table, you will have to round it to whatever decimal your table will go to. So the table that I'm using only goes to 2 decimal places, so I am going to round my z-score to negative 0.54. And this right here, this is my test statistic. Now you would have to choose to go by the p-value method or to go with the critical value method. I'll do each of those very quickly. So if we wanted to do the p-value method, what we would do is we would sketch our normal curve. We know that this is a two-tailed test. I know that my test statistic is negative 0.54. Well, because I have a two-tailed test, I also have to consider the upper portion here, which would be at positive 0.54 because we have symmetry. Then I go to my normal distribution table and I look up the area to the left of my first test statistic here, negative 0.54. And that area is 0.2946. Now I'm going to copy that area up here because I do have a two-tailed test, so 0.2946. And then to find my p-value, it is the total area of my rejection region. So I would take the area of my right tail and the area of my left tail, add them together, and I get a p-value of 0.5892. Then I can compare my p-value to my alpha, and our little saying is that if the p is low, the null must go. So I have to decide 0.5892, I'm checking, is that lower than my alpha value? Well, if I come back over here to my list, my alpha value was 0.05. Well, 0.5812 is not less than that. So in this situation, we would fail to reject our null hypothesis. So that's one option. Now, if I go by and do this as the critical value method, I am going to still draw my two-tailed test, but this time I take my alpha value here of 0.05 and I am going to put that in my as the area in my tails. But because it's two-tailed, I have to split my 0.05 in half because I need my total area to be 0.05. So each tail is going to get 0.025. Then what I do is I go back to my normal table of z-scores, and I'm going to look up the z-score associated with these two locations. Well, the z-score that I get is negative 1.96, and then this would be positive 1.96 because of symmetry. Then I can take my test statistic, because this is a z-score, and my values right here, my 1.96 and my negative 1.96 are also z-scores. So I'm going to compare those values. And if I just kind of plot this z-score, negative 0.5, well, 0 is right down my center. So negative 0.5 is right about here. And we can see that that falls in our non-rejection region. So we would fail to reject the null hypothesis, which is the same answer that we got over here. Once we make that decision to fail to reject the null hypothesis, then we can go ahead and write our full conclusion. And remember, there are many ways that you can write these conclusions. So if this is by no means the only way to write the conclusion, but here's what I had written, is that we do not have sufficient evidence at the 0.05 significance level to reject the claim that the proportion of four-year college graduates that have student loan debt, oh, that should be an N there, is 71%. Basically, we don't have evidence to say that the proportion of four-year college graduates with student loan debt has changed since the 2012 rate of 71%. Okay, so that's kind of how you do a single proportion by hand. And I showed you both the p-value method and the critical value method. Now, if you are going to be using technology, my guess is that you would probably use the p-value method. Now, we're going to use StatCrunch. And in StatCrunch, our menus that we are going to go to, we're going to go to the stat menu, we're going to go to proportion stats, and then we're going to go to one sample. And at this point, depending on the problem that you have, you would either select with data or with summary. We are going to choose with summary because we don't have the raw list of data. We just have the final numbers that 93 out of 135 said they had debt. So that would be a summary. Okay, and I'll show you how to do that. So here we are in StatCrunch, and we need to go to the Stat menu, Proportion Stats, one sample and with summary in order to do our problem. Pops up this window and it asks us for the number of successes. So for us, that was the 93 students that said yes, they did have a student loan debt. Our number of observations was 135, and we want to perform a hypothesis test. Now notice here our null hypothesis will default to the population proportion equals 0.5. We need to make sure we change that 0.5 to match what our null hypothesis was, which is 0.71. And then here we need to pick the symbol that matches our alternative hypothesis. Well, for ours we were interested in not equal, so we are going to choose the not equal. Then we can press compute. Okay, and we can see here that we have our test statistic, which we calculated by hand right here, negative 0.54, and then our p-value of 0.5888. Now you will notice that our test statistic and our p-value are slightly different from what we computed, and the reason for that is because when we did our hand computation, we had to do some rounding. So these values would be more accurate than our hand computation ones because the computer program would do less rounding.